Hey guys, we're going to do a few more lessons today. What I want to do first, hopefully you can take a screenshot of this. That is the answers to 8.2 and 8.3. If not, I'll probably send a text with these on it. With the text, I'm going to send the answers to the worksheet that you're going to do after all this is done. This is just a practice worksheet. So I'll try to send a text with those two. If you don't get it soon, hopefully one of you can kind of remind me. We already went through the geometric series, P series, Kth term, harmonic series, integral test, and so now we're going to go to the others. So we're just going to pick up with 8.4. It's called the comparison test. Now what's going to happen is just like all the functions that we know, you add and subtract, and then you move them around, and you can expand them and shrink them and do all that. Well, the same thing kind of happens with this when we start comparing them. So this is what the comparison test says. If you have two sets and then every element of one is less than the other, that's the key, is one set smaller than the other. If the bigger set converges, then the littler one's going to converge also. If the bigger set adds up to be one number and we have a set that's smaller than it, it's going to add up to a number also. So that's one thing. The other says that if A sub k, if that diverges, then B of k is. So if your smaller set diverges, then the bigger set's definitely going to diverge because it's bigger. Now, you can't go the other way with this. So if AK converges, it's smaller. We can't say anything about BK. And if BK diverges, we can't say anything about AK because, just because this one would diverge or converge doesn't mean this one does. But if the bigger one converges, then the smaller one must converge, but it doesn't work the other way. If this one converges, you can't say anything about the bigger set. Likewise, if the bigger set diverges, then the smaller set, if the smaller set diverges, then the bigger set's going to diverge also because it's bigger. But if the bigger set diverges, we don't know anything about the smaller one. So how are we going to use this? We've been doing the P series and the geometric a lot. So when I look at this, I can say, hey, I want to find if this series converges or diverges. So the sum of 1 to infinity of 1 over 2 plus 3 to the n. You should kind of recognize this to be like 1 over 3 to the n. This is really like 1/3 to the n. So this is a geometric series, and if your base is smaller than 1, I know that this thing is going to converge. And so all you have to do is you just have to ask yourself, is this always smaller than that? Well, is it? If you pick any n, like 1, this will be 1/3, that'll be 1/5. The denominator, when you add 2, is always going to make this guy smaller than this one. So if you can show that and just say, hey, this one's always bigger than this one, if the bigger set converges, we can say that this converges by comparison test. And so that's all you want to do. Now, likewise, if you wanted to prove that, if it's going to diverge, you just need to prove that the smaller one is still smaller. So if this diverges, then that one does. So what we've just proved is, hey, my bigger set converges because it's a geometric series. Now the smaller one must, because I know that this one is bigger than this one. So that's the comparison test. You don't really need to know the comparison test that well because you can almost always use the limit comparison test. What does the limit comparison test say? It just says that if you have two series and they're both positive, that's the key, it's not one of the alternating, and you look at the limit as k approaches infinity of one series over the other. If that limit is a number that's bigger than 0, then both these things are going to do the same thing. They're both going to either converge or they're both going to diverge. In this case, when I look over here, my first thing is I wanted to do the comparison. Well, 1 over 2n is really like 1 over n with a 1/2 out front. That I know 1 over n is the harmonic series and it diverges. So my bigger set diverges, so I can't use my comparison test. But what I can do is I can compare this to 1 over 2n, and I can do the limit comparison test, because 1 over 2n, I know this is going to diverge because of the harmonic series, or you could say P series, because P series means that it's n to the first power. And if this is 1 or less, it diverges. If it's bigger than 1, it's going to converge, if you go back to the little chart we have. So I know this is the case. So what I do is I come here and I said, you know, I just need to look at the limit as n approaches infinity of this guy over this guy. When you divide by a fraction, you convert, you invert and multiply. So it's going to be 2n over 2n minus 3. This limit as n approaches infinity because my degrees are the same. It's the ratio of the lead coefficients is 1. Since 1 is bigger than 0, I know that these two series do the same thing. Because I know 1 over 2n diverges, that means that this thing is going to diverge also by the limit comparison test, which sometimes I'll just put LCT. All right, so that's the comparison test, and that's the limit comparison test. All right, we're just going to keep moving on. The next is going to be the alternating. And if you read under it, it's going to say alternating with an absolute versus, anyway, it's going to say conditional or absolute, but we're going to talk about what that means. The alternating one is the easiest to spot because for the alternating series test, you're always going to see a -1 to the n or a -1 to the n plus 1. That's how you're going to recognize the alternating series test. So what you want to do is, the idea is just going to be this. You're going to have one of these two, and it doesn't matter which, with some function here. Here's the thing. This, okay, if you want to read your little thing, just so I can follow, so you can try to read this, it says alternating comparison test. If the limit as n approaches infinity of this is equal to 0 and AK is decreasing, that means the series converges. Okay, so what we're going to do is we just look at AK and I ask myself, is this a decreasing function? And that's really all you're looking for. Is this thing a decreasing function? And if it is, then we know that this is going to converge. Now, there's going to be two types of problems. One of them will say absolute converge. And then one of them is going to say a conditional. Hey, the difference between these two is just this. This guy right here. If that happens to be something that the limit diverges, then it's going to be an absolute diverges. If this thing converges, it's an absolute converges. If this guy right here is something that diverges, that on its own it normally wouldn't converge, then it's called conditional. This thing is only going to converge because of this, because of the alternating signs, because a to the k in itself wouldn't. So let me give you a couple of examples of what I mean by this. So here's one. -1 to the n of 1 over n squared versus -1 to the n of 1 over n. Let's just look at these two, and we'll say that n is going to go from 1 to infinity. So here's two different series. The question is, do they converge or diverge? That's really all I would need. If you put these, I may even give you some extra credit. So what you're asking yourself is, you recognize this alternating signs because of the -1. Now we look to the function. Is this thing always decreasing? Meaning, as n gets bigger, is this thing getting smaller? Well, yeah, it's going to be 1, 1/4, 1/9. This guy's going to be 1, 1/2, 1/3. They're decreasing. Once they're decreasing, I immediately know that they converge. And you can say, yeah, it converges because of the test. Now to check to see if it's absolute or conditional, we look to this guy right here. And we say, okay, is 1 over n squared, does that normally converge on its own? Well, that's going to be a p-series, right? 2 is bigger than 1, so this thing converges on its own. If it converges on its own, that means we have what's called an absolute convergence. To where if this guy doesn't converge on its own, we know that this normally diverges. That's the harmonic series. It's the p-series with 1 as the exponent. Because that normally wouldn't converge, it would diverge. Now it's a conditional convergence. The only reason why this one converges now is because of the alternating signs. So for the alternating signs, it's really pretty easy. You'll recognize it by -1 to either n or the n plus 1. And then you just look to this. As long as this is decreasing, we can apply the test. And then if it's an absolute convergence, that just means that my original thing would have converged on its own. And if it would not have, we say it's called a conditional. Okay, two more tests, and then we'll talk a little bit. Okay, last two. One's called the ratio test, and then one is called the root test. First of all, these are going to be the last ones you kind of look at, but they're going to be easy to recognize. You're going to use this if there's a lot of exponentials or factorials. So exponentials and factorials is when you want to use the ratio. The root is if you ever have a power to a power, that's going to be an easy recognition. Okay, we very rarely see this. All right, so that's going to be how you know when to use each of them. So let's talk about the ratio. The ratio, I'll just read this off so you have this in front of you so I don't have to write everything. The limit ratio test for absolute convergence. So we look down here and it says the limit, so we're going to look at the limit as k approaches infinity of a to the k plus 1 over a to the k. And that's going to equal some number, okay? Depending on what this number is, tells us what happens. If it's less than 1, it's going to converge absolutely. If it's greater than 1, it diverges. If it's equal to 1, it's inconclusive for us, all right? So we need to be able to find the limit of the k plus 1 term over the k term. So let's talk about how to do that, and there's a little algebra involved, so I want to make sure you're okay with this. So here's an example. We have 2 to the n over n factorial, and I just want to go from n is 1 to infinity. So the idea is, hey, here's a series. Does it converge or diverge? If you see factorials and exponentials immediately, you know there's a lot going on here. Now, if you remember what I told you about limits and stuff when we talked about L'Hopital's rule, before you even use that, if the numerator is growing faster than the denominator, you can immediately say it's going to infinity. Remember, this is the most growing one. So n factorial grows the fastest over an exponential. So this limit in general is 0, so I can't use the k-term test. If this was flipped around and I had n factorial over 2 to the n, I can immediately stop and say, hey, that's going to diverge because the limit is not 0. If n factorial is on top, it's growing faster and faster. It'll never converge. But in this case, I look at this and I'm like, hey, I don't know how to do this. So now I need to look here. So how do I do a to the k plus 1? You just come up here and you put n plus 1 in everywhere you see an n. And then what you're going to do is you're going to put that over this. So I need to take the limit as n approaches infinity. How do you do this? Well, real quick, just remember, 2 to the n plus 1 is really 2 to the n times 2, because you can take the 2 to each, and these two are the same. Factorial means that you take n plus 1 times everything down to 1, which is really n factorial times n plus 1. So you can replace you can replace 2 to the n plus 1 times 2 to the n times 2, and n plus 1 factorial by n plus 1 times n factorial. Now, when I look at this limit, as n approaches infinity, when I divide by a fraction, I multiply by the reciprocal. And if you look, the n factorials, and that cancels out. So now I'm looking at the limit as n approaches infinity of 2 over n plus 1. Well, if my degree on bottom is bigger and I'm approaching infinity, this limit is 0. So I go to my chart, and if I look, this says that, hey, if my limit is less than 1, which 0 is less than 1, it's going to converge absolutely. And then you put by the limit ratio test. Okay, this is going to be some hard algebra. If you need to text me or FaceTime me or something to walk you through some of it, feel free to. Okay, Good thing is you can rewind it and go back over that. Now, the last thing is the root test. You're going to notice this because you're going to see into and in power. Now, let's look at the test real quickly again so you can see it. The limit root test for absolute convergence. You're going to look at the limit as k approaches infinity of the kth root of this. So what you're going to really do is you're going to take the kth root, and that's going to end up eliminating this root right here. And then once again, we just read what happens to my limits. So I need to find the limit as of the square root of whatever my series is. So I'm going to go ahead and just throw an example out here. So I'm going to have e to the 2n over n to the n. And I'm going to say n is going to go from 1 to infinity. So the question is here's my series. There's a lot going on, but the recognition is the n to the n. If you see something like that, the only way you can do it is going to end up being the limit root test. So what we do is we look at the nth root of my series. Well, just remember, this is really the 1 over n power. So if you take e to the 2n over n to the n, and then we raise it to the 1 over n power, when you raise a power to a power, you multiply, and you end up with e squared over n. That's going to be my new function when I take the root of it. So I'm looking at the limit as n approaches 0 of e squared over n. Well, e squared is a constant, so the degree on bottom is bigger, so this is 0 once again. So I look to my chart and it says, hey, if this is less than 1, it's going to converge absolutely, and you put by the limit root test. Okay, that's a lot going on, I know. This is uncharted time, so just bear with me, but keep in touch. Zach's been texting me a lot and asking me over email, so I've been helping him, and a few of you others have. So if you need anything, feel free to just text me. Thank you.